So how computers quote-unquote see is by recognizing things in a field view. But how can it recognize and distinguish different information from each other? How do you know what the moon looks like? And how is that different from the sun? How would you teach someone else what the moon looks like? And how would you teach them to tell the difference between the sun and the moon? Same principle here. You want to treat the computer as a toddler who has never seen whatever object you want to train them to identify. And you first feed it a ton of data to show examples of what that object can look like, and corresponding answers to let them know what exactly that object is. The computer would take the answers to all this data and analyze the pixels and patterns to predict what the answer should be next time a new value is fed into it. So for this exercise, we use two components to teach a computer how to see: data and labeled images. Now, disclaimer, we'll be using already made exercises since simply creating data and models from scratch is just too time consuming, and the point of this TD is just to expose you to the concepts of machine learning. So go ahead, open a Collab and import the notebook by clicking Upload and Browse, and then locate your TD2 folder, and then open up Fashion MNIST. Now for this exercise, we don't need to import a separate dataset into the notebook like the other exercises, since Collab already has the Fashion MNIST and its sample data already loaded. You can see it here under sample data, and then MNIST. So Fashion MNIST contains 70,000 images labeled into 10 categories, and even though each of the images are small, being 28 by 28 pixels, they're still able to be recognizable to us, and also recognizable enough to train a neural network on. So go ahead and execute the first cell to import TensorFlow. And again, we'll use the Keras dataset to load the data into a single line of code and the dataset Fashion MNIST. In the second line, we'll use the computer to return 4 values. We're splitting up the images into 2 sets to train the neural networks on, one of them, and then test the other one on images it's never seen before. A set of training images and training labels, and then a set of test images and then test labels. We're splitting up the images into 2 sets to train the neural networks on, one of them, and then test the other one on images it's never seen before. Dividing by 255. Now execute the cell. The images will be 28 by 28 pixel arrays of clothing items labeled 0 to 9, and that indicates the appropriate category the item belongs to. This way the labels can be used universally, and they're not going to be dependent on one specific language, like English. And that's why machine learning is so great. If we wrote, let's say, a spelling corrector by hand in English, in order to have different versions of it in other languages, we would have to code each one from scratch in each language. But with machine learning, all we need to do is collect the data in the specific language, and then we can use the same machine learning model. So when you execute the cell, and then the next cell, you can visually see an example of this data set. And can you guess what it is? And these numbers are on a grayscale, but the numbers are values between 0 to 255, 0 being the color black, and as you can see up the top here, all these zeros will be shown visually as black. Dividing by 255. Now execute the cell. And at the bottom is a colorized image of the boot, but the transitions between light and dark colors correspond to the light and dark grayscale on the numbers above. The darker ones lean towards 0 and the lighter ones lean towards 255. That's just how the machine gets its vision. By converting pixels into numbers it understands, it can take in and analyze what we normally see. So we need to normalize the data for the model for it to work its best. The neural networks work best when it's working with numbers between 0 and 1. And since the pixels of this image range from 0 to 255, we'll normalize this image by we're layering different layers of thin. So one would be the flattened layer, which is going to flatten the data to feed into the dense layer. And then we have two of these dense layers, one for 128 and another for 10. Go ahead and run that. Dividing by 255. Now execute the cell. And then we're going to define our neural networks model. We're layering different layers within. So one would be the flatten layer, which is going to flatten the data to feed into the dense layer. And then we have two of these dense layers, one for 128 and another for 10. Go ahead and run that. And then compile all this data into the optimizer atom in the next cell along with the loss function. We're going to also fit the training images and labels into the model and do 5 epochs for this training. So run the cell. The runtime, you can hit runtime up here, change runtime type, and make sure that it's set to GPU. Okay, paste the results of the last cell into your answer sheet. You restart, but it's going to make it load faster. Analyze the results of this output is that we look at the accuracy, and it shows us that the model was right about 88% of the time in categorizing these images. The loss and optimizer function made it so that with each epoch 1, 2, 3, 4, 5, it's increasing its accuracy by making a more improved guess based on the accuracy feedback. So at first it started out about 82% correct, then 86, and then it worked its way up to 88%. Now to test it on images that's never seen before, we're going to pass the parameters test images and test labels into the model. And when we run the cell, the machine tells us that it was accurate about 87% of the time after comparing its training to its testing accuracy. Okay, paste the results of the last cell into your answer sheet.